So we want to use what we learned from the previous sessions, and in the past, from the past, like we want to graph this following functions with all of these question 1 through 7 answer. Okay, and on the test probably I will basically ask you to do all of them or most of them. Okay, your textbook may not ask all of them, but you know, hey, just for the practice. So first thing is like finding out the domain. So the domain, I can see that denominator cannot be equal to 1, right? So I would say that my domain of this functions, right, is basically everything instead of x such that x is already a number, except x cannot be equal to 1. That's my domain. And then the second part is finding out the intercept. So for intercept, the easiest one is like for this one, I'm going to let x be equal to 0. Right? To find out my y-intercept. So that will become y equal to 0 over 0 plus 1. I should say 0 to the third power minus 1. So it's still going to be equal to what? 0. So therefore, the intercept is 0, 0, which is both x-intercept and y-intercept will be the same. So I don't need to further find out anything anymore. And the third part is asking for axis of symmetry. The axis of symmetry is basically what you substituting, you know, with negative x and then see what you get from there. So when I substitute negative x into this, you know, particular functions, x to the negative 1 to x to that. So this will give me negative x over negative x to the third minus 1, which is going to become x over, right, x to the third plus 1 after I factor out negative 1 and reduce it. So that basically tells me it is not the original equations. So, and I don't have a negative factor either. So therefore, this will be what? Neither functions, right? So it's not symmetry about the x-axis, y-axis. And the fourth is asking for the asymptotes. So we're going to look at the horizontal asymptotes and the vertical asymptote. So according to the definitions, horizontal asymptote is basically what as x approaches to infinity or x approaches to negative infinity. You need to look for both limits, okay? Because sometimes you may have two horizontal asymptotes depending on you go into infinity or negative infinity. So let's find this as horizontal asymptote first. So when we find out the horizontal asymptotes, right, limit as x approaches to infinity of the functions, then by using the techniques, we found out that the limits will be 0, right? And right here, I multiply, you know, from to the second step, I multiply numerator and denominator by 1 over x to the third power. Similarly, I have to also check, you know, limit as x approaches to negative infinity. And using the same technique, my limit is 0. Since both of the limits are the same, right? So we're only going to get one horizontal asymptote, which is y equal to 0. If going to positive infinity limit and going to negative infinity limits, if they are different, then that basically means that you will have two horizontal asymptotes. In some of the homework problem, you will run into that kind of situations. Okay? And for the vertical asymptotes, according to the domains, I already know that the vertical asymptotes is equal to x equal to 1, but we want to go a little bit further, checking out the behavior, right, around this vertical asymptote. So I look at it, limit as x approaches to 1 from the positive side, and then of the functions, and this tells us it's going to go to positive infinity directions, and limit as x approaches to 1 from the left hand side of the functions, and that tells us it's going to go to negative infinity directions. So number 5 is asking you to find out the increasing, decreasing intervals. And number 6 is local maximum, local minimum. Number 7 is like concavity, concave up, concave down, and point of inflections. So to do this 5, 6, and 7, we need to know our first derivative and the second derivatives, right? So before, we answering all of this question, let's take the first derivative and second derivative from here, and then using the first derivative, second derivative test to answer those questions. So when you take the first derivatives, right, using the quotient rule, and the result after you simplify it, we got this negative 2x to the third minus 1 over x to the third minus 1 to the second power. Now, when we take the second derivative from here, again using the quotient rule, and after factoring out negative x to the second power and x to the third minus 1, and then simplifying a little bit, we got the second derivative to be negative 6x squared times with negative x to the third minus 2 over x to the third minus 1 to the third power. Remember, this x to the third power minus 1 and one of the denominator reduce it. Then next step, what we need to do is we need to find out, right, when the first derivative is going to be equal to 0, or when the first derivative is going to be dne, right, to get our critical number. So let's find this out. So when y prime is equal to 0 or y prime does not exist, then we know that those x value, that will be a critical number. So first setting up y prime equal to 0, and then what I solve for x, that gives me negative 1 over cube root of 2. And y prime does not exist at when x is equal to 1, because the denominator will become 0 and it will become undefined for y prime function. Right? So that means like the function y prime does not exist. But however, we cannot consider this as a critical number because x equal to 1 is not in the domain of y, which is original function, right? Because remember, why are we looking for critical numbers, right? Because that's where it's going to happen in either local maximum or local minimum. If the original function does not even define at that particular x, we cannot graph anything. So there will not be local max and local min. So therefore, my critical number is only what? Negative 1 over cube root of 2. And so using that, right, to find out, break it down into interval, right? So we have this negative 1 over cube root of 2, which is approximately 0.079, 0.79. And then we need to put in the vertical asymptotes or the dne part, so that I can check my values of y prime in each interval. And when you pick a number on each interval and test it, you got increasing right here and decreasing between negative 1 over about 3 and 1, and decreasing anything beyond positive 1. So now I can answer my number 5 questions. So y is increasing, right, on the interval from negative infinity to negative 1 over cube root of 2, and y is decreasing, right, on negative 1 over cube root of 2 all the way to positive infinity, because you can basically write it down like this. Okay. If you do that, or if you're looking at this and if you do that, then basically what's going to happen is you will get points off. Remember that 1 does not define in the original functions. So if you write like this, that means like 1 has like some value to it. So it will be wrong. So technically you should write it down as up to 1 union with 1 to positive infinity. You need to make sure that it does not include 1 in the increasing and decreasing interval. Any questions? From part 5, and we know that at this critical number negative 1 over the cube root of 2, it will change it from increasing to decreasing. So we're going to have a local maximum by first derivative test. So now I can conclude this way. This is important. You need to tell me which test you are using, right? By first derivative test, right? We have local maximum at what? F of -1 over cube root of 2. And we want to find out what is the local maximum value is. So using the calculator or, by hands, so try to compute that. Okay. So once you calculate it, right, put it into the original functions, y functions, then my output value will be, again, -1 over cube root of 2. So therefore, this is the the local maximum point. So the next, what we want is to find out concave up and concave down. So those concavity, interval concavity, in order to talk about interval concavity, first we need to find out when the second derivative is going to be equal to 0, right? And then also testing like this right here, we need to test the second derivative value to see which interval will be positive and which interval will be negative so that we can talk about concavity on this part, right? So let's try to find that out first. So setting up y double prime equal to 0, and I got two possible point of inflections, which is what, x equal to 0 and x equal to negative radical 3 over 2. We also need to check when the y double prime is not going to be exist, right? So once again, if you look at this functions right here, this formula right here, which is the y double prime formula, again, x cannot be equal to 1. So we got this point right here. And the reason why you need to look at this is because only if you find out both zeros and the DNE part, then you can properly put it all the info in on the real number line. Okay? And once again, for this x equal to 1, it cannot be point of inflections, right? Because remember, these are all possible points of inflections after we check the concavity. So this cannot be point of inflections because once again, x equal to 1 is not 1 is not in the domain of what y function, which is our original function. So now that we have like these values, so I'm gonna put it on a real number line and then test each intervals, right? Pick a number on each interval and test it, and this is what we get. Right? So from negative infinity to negative cube root of 2, that is concave up, and also 1 to infinity, that is concave up. So that will give us one answer, which is negative infinity to negative cube root of 2, union with 1 to positive infinity. That will be concave up. And the next will be what? Concave down, right? Concave down between negative cube root of 2 all the way to 1. And since 0 is in the domain of the original function, so I can basically write down my concave down will be negative cube root of 2 all the way to 1, right? Not like before, I don't need to separate it in this case. Finally, point of inflections, you need to compute this negative cube root of radical 2 into the y functions, right? So what do we get from there on? So let's do the computations. So the first thing is we want to look at, change something that I made a mistake on a computational part. So my local maximum, when I compute it, it cannot be a negative number, right? So I made a mistake right here. So this is wrong. After you compute it by hands or calculator, this is the local maximum output value, cube root of 4 over 3, or approximately 0.5291, so on and so forth. So we're going to be using 0.0, uh, 0.8, negative 0.8, and then 0.5, right? Approximations of this. So when we are graphing using all of this, right? First, we're going to put our vertical asymptotes at negative, positive 1, horizontal asymptote at 0, and then my x-intercept and y-intercept, which is right here at 0, 0. And then I have my local maximum point right here, okay? And then I have my point of inflections right here. And also we know that what's happening on the behavior around the vertical asymptotes. So it will be approaching to 1 from the left-hand sides is negative going to negative infinity. Approaching to 1 from the right-hand side is going to positive infinity. And since this is a horizontal asymptotes, my graph is going to be what? Approaching to 0, right? As x become bigger and bigger number, and as well as x become larger and larger number. And how do I know that this graph is going to be above the x-axis? Because as you go to infinity, I don't have any other x-intercept anymore, right? Or go to positive infinity, I don't have any other x-intercept anymore. So the graph will not pass through the x-axis and come back up around this asymptote. So when I graph this, right, and using the concavity part, and we know that, so from 1 to positive infinity is concave up. So therefore, I can basically connect this part, which is this is going to be concave up like this. Right? It's going to be concave up 1 to infinity. And we also know that it's going to be concave up negative infinity to negative radical 3 over 2, which is up to point of inflections, is concave up. So therefore, the graph right here, I will try my best right here, right, to graph it. So this portion, I'm going to be connecting with this. So this portion is going to be concave up to here. So my graph is going to be going like this. Right? So it will be curved up like that. And then between negative radical 3 to negative cube root of 2 to 1, that is concave down. So the rest of it is concave down, and then go connect with this going to negative infinity direction. So it will be going like this. Concave down, and then passing through the horizontal asymptote, and then connect like this. And this will be the sketch, and also almost close to a precise graph, because like we are all precisely doing all the concavity, right? And then increasing, decreasing will fall after that. Right? And this is our end of example 1. So example number 2, we want to do 1 through 7 again, but this time using the an equation that involves trigonometric expressions. Right? The good thing is we don't want to graph like endlessly, so giving you a particular interval to graph it. So therefore, that makes it easier for us to talk about the first part, which is my domain. Right? It will be just basically simply between negative pi over 2 to pi over 2. So you may write it down in interval notations or separator notation for the domain part. Either one is fine. I don't really mind, right? And second is finding out the interceptions, right? Intercept. So to find out the intercepts, the easiest one is like let x be equal to 0 first, and then from there on, what is my y, right? Intercept's gonna be. So in this case, when I let x be equal to 0, my y is become x times 0, 2 times 0 minus tangent of 0, so which is equal to 0. So we got what? 0, 0 origins again. So therefore, I don't need to find out, anything else further than that. No, I should say like there's only 1 so far, so I need to let I'm not sure my x-intercept is only 1, so let y be equal to 0 to find out what is my x-intercept is, and that basically becomes 0 equal to 2x minus, right, tangent of x. So that's where you're gonna have to like try to use all the technique that we learned in the past to try to find it out, right? So let's try to look at this. Place the negative x into it, and that will become 2 times negative x minus tangent of negative x, which will give me negative 2x. And since tangent is an odd function, so this negative can bring it out, so this will become plus tangent x. So when I basically factor it out on negative and then see what we will get. So 2x minus tangent x. So basically we got what? A negative of y of x. So this basically tells me it is an odd functions. So right, y is odd functions. And that basically tell me symmetric about origin. So that's symmetrical that we have, okay? And then after that, we're gonna talk about the asymptotes. And since this is a periodic functions, we don't have a horizontal asymptotes at all, right? We won't be able to find horizontal asymptote. But we do have a vertical asymptote because like, tangents, negative, we already see that from this domain, negative radical, negative pi over 2, pi over 2 and then pi over 2. Those are our vertical asymptote. So let's check on that part, right? So within this, negative pi over 2 to pi over 2, this function doesn't have a horizontal asymptotes. There's none. But we do have a vertical asymptotes when x is equal to negative pi over 2 and then pi over 2. So what we need to check is check on what's happening on behavior around this vertical asymptotes. So therefore, we look at limit as x approaches to negative pi over 2 from the right side, right? And we know that the tangent graph, right, when it approaches to negative pi over 2, tangent graphs give you a very large negative value. So negative and negative become positive. So it will become a positive number with this 2x is going to be a smaller value. So when you added up those two values, this will give you what? Infinity. Okay? And when limit as x approaches to pi over 2 from the left-hand side, and we know that from the tangent graph, this is going to be going up to what? Positive infinity. And this will be a constant right here. So a constant minus a positive infinity, that will give you what? A negative large number. So that's what we found out on the behavior around those two. And when we talk about, 5, 6, 7, like in the other example, we need to find out, first derivative and second derivatives before we can talk about increasing and decreasing local max and local min and concavity. So let's try to find out, the derivative first, and after that, let's look for what we want. Okay. So when we take the derivatives, right, of the functions, the first derivative, that will give me 2 minus secant square x. When you take the derivative again on the second derivatives, then after you simplify it, you will get negative 2 secant square tangent x. So to answer part 5, we need to find out the critical number first, which is when the y prime is equal to 0 or y prime is dne. So when y prime is equal to 0, when I set it up equal to 0, so we got secant x is equal to plus or minus square root of 2. So which x value will give, secant square root of 2? That will be at the measurement of the angle pi over 4 and negative pi over 4. And when will this secant x will be equal to negative radical 2? That will be pi over 3 pi over 4 and then 5 pi over 4. But however, our domain is only between negative pi over 2 to pi over 2. So therefore, these two cannot be our critical numbers. So using pi over 4 and then negative pi over 4, along with the endpoints, which is not included, negative pi over 2 and pi over 2, and we are testing the value of y prime, right? The first derivative value. So that gives us, decreasing between negative pi over 2 and negative pi over 4, and pi over 4 and then pi over 2, and then increasing on negative interval of negative pi over 4 to pi over 4. So that's how we got the increasing and decreasing of this functions. And from here, we can clearly see that, where is our local maximum and local minimum is going to be. So my part 6 will be, right, by first derivative test, right? By first derivative test, we will have local maximum at y is equal to pi over 4, and we want to find out that value. And we will have local minimum. This time we have both local max and local min, right? At what? Right here from decreasing to increasing, so at negative pi over 4. And we have that. So let's find out this, two values before we move on and continue to next. So after you do the computation, that will be pi over 2 minus 1 for the local maximum output value, right? And so the order pair is approximately that. And local minimum will be negative pi over 2 plus 1. That will be the function value. So approximately then this order pair. So the next part is like we want to find out the concave up and concave down. So we need to set the second derivatives equal to 0 and then solve for, possible inflection points. So, and then using the same idea on the real number lines, we're going to try to test the second derivative values to talk about the concavities, concave up or concave down. So let's try to do that first. Okay. So when we set the second derivative equal to 0, right? And we have negative 2 sine square x tangent x equal to 0. So we can set secant square x equal to 0. And we know that the secant will never be 0. So therefore, this is no solution. And tangent of x equal to 0, that's only going to happen when x is equal to 0 degree. So one more thing that we need to check is y double prime does not exist. And because of both secant and tangent is going to be undefined, right, at negative pi over 2 and pi over 2. So those are the, the x value that's going to make the second derivative does not exist. But however, since these two values are not in the domain of my original functions y, so therefore these cannot be considered as possible points of inflection. So we only have one possible point of inflections. So plug it in all these three value that we get into on the real number line and then find out the value of y double prime. I got from negative pi over 2 to 0 is concave up, and 0 to pi over 2 is concave down. So basically you are choosing a value from each interval and then test it into what? This second derivative functions right here. Okay. So that gave us concave up and concave down. Because of the concavity change at 0, we have a point of inflections at 0, which is y equal to 0. And now let's use all these informations to graph our functions. Okay. So my y-intercept and x-intercept at 0, 0, and this is also my points of inflections. And we already talked about local maximum and local minimum and with approximate decimal number, which is going to be 0.8 and 0.5, all right? And the local minimum is negative 0.8, 0.5 right here. And from the behavior around the vertical asymptote that we found out is when you approaches to negative pi over 2 from the right hand side, it's going to positive infinity. And when you approaches to pi over 2, right, from the left hand side, it's going to negative infinity. So now using the concavity, we know that it's going to be concave up from negative pi over 2 to 0. So therefore, I'm going to be trying to, graph like this, concave up. And then from 0 to pi over 2 is going to be concave down. So it'll be a peak right here and then go back down and then get this. So this is the sketch that we can get right here. Okay. So that will be the graph of this second example.